Hello everyone, and welcome to my walkthrough of question 13 of the Spring 2019 MAS1 exam. Let's get started. You use the inversion method to simulate two random variables x from a Weibull, theta, tau distribution using two independent draws u from a uniform distribution on 0, 1. The results of this simulation are shown below. For I equal 1, x subscript I equals 416.28, u subscript I is 0.5. For I2, x subscript I is 357.36, u subscript I is 0.4. Calculate the value of theta used to perform this simulation. In this problem, there's really only one thing you need to know, which is what the inversion method is for simulation and how to go about using it. So to start off, just kind of want to walk through about the concept. So here, this is using the final results we end up determining. This is the distribution we end up aiming to simulate. So this is the PDF, and what I've done here is just break it up into deciles. So each of these sections is 10% of the distribution. So if you were to calculate the area under the curve for each of these, they would each equal 10%. And so that's why it's narrower towards the middle and wider towards the outside, because they occur less frequently. What we can then do is, instead of considering the PDF, we can consider the CDF, and those have one-to-one mappings. And so here, the area under the curve doesn't really mean anything, but we do care about the y value. So again, this is just going up by increments of 0.1, and I have that shown by these gray horizontal lines. So for the inversion method, because the CDF is bounded in between 0 and 1, and there's only one value that corresponds, one y value that corresponds to each x value, this is a method we can invert as opposed to the PDF. Also, it is ranging from 0 to 1. So for the inversion method, you use that uniform between 0 and 1, and that has a one-to-one mapping. So here, I just have illustrated that uniform distribution broken up into 10 sections, and you can see how they correspond to each value on the CDF. So if you were to randomly simulate a value of, let's say, 0.95, you would then go to the CDF curve, look at 0.95, follow that over, it intersects here. You would then go down and say, oh, that value corresponds to an x value of 900. And that's how you would go about simulating an x value of a distribution using nothing but your understanding of the CDF, as well as the ability to randomly generate uniform values. So with that understanding, we can then jump into the problem, which is a bit backwards. This isn't what you would do in practice. They're just testing your understanding. So they're giving us the simulated results, and then we're trying to back into the parameters of the distribution. And since they give you these two values, kind of start off thinking there's probably going to be some systems of equations or something to that effect, but I think we end up being able to divide out one of these terms. So the very first step is knowing what the Weibull CDF is, or I guess it's to know that you want the CDF, not the PDF, for the reason we spoke about earlier of its values range from 0 to 1. And for inversion method, you're always going to be dealing with the CDF. So going into your formula sheet you're provided, you're going to find this formula. Let me see if I can zoom in a bit here, since those are some pretty small values. So 1 minus e to the power of negative x over theta to the power of tau. So we now know what the CDF is, and we know that when we plugged in a value of 0.5, when we simulated a value of 0.5, that equaled 1 minus e to the power of negative x, and the simulated x value was 416.28, and then there's this theta and tau. We then can do the exact same thing with 0.4 down below, so we simulated a uniform 0.4, and then that resulted in a simulated x value of 357.36, along with the rest of this mess. And then just to simplify what we end up doing, which is we can divide things out to remove a term, we're just rewriting this. So let's see what we're doing. Subtracting 0.5 from both sides, then adding this mess over to the right, and then taking the natural log of that value. Gets us this 0.6931 and leaves us with this more simplified form here. We do that with 0.4 as well. And then what we can do is say, let's divide by each side of the equation. So 0.6931 divided by 0.5108 should still equal this quantity, which equals 0.6931, divided by this quantity, which equals 0.5108. The reason we do this is we can then pull out these theta terms. So simplifying this mess on the left, we can pull out both of thetas to the power of tau, but theta over theta is just 1, and that's a clever way of getting rid of one of those terms. And then all we're left with is this fraction to the power of tau equals 1.3569. And then finally you solve tau equals the value of 2. Then we know tau is 2. We can just go back to one of these equations, it doesn't matter which, but I use this equation here. Plugged in tau equals 2, solve for theta, and we get that theta equals 500. Scrolling back up, we see that 500 falls in the range of C, so that is our final solution. Thank you for watching this video. If you find these videos helpful, please consider subscribing. Thanks, have a good one.